It's my pleasure to introduce our speaker today. Our speaker is Youngheng Yang. He received his Bachelor of Engineering degree in 2009 from Northwestern Polytechnical University in China. After graduation, he worked at Southeast University in Nanjing, China, on modeling and control of single-phase grid-connected photovoltaic systems. In 2003, he serves as a visiting scholar in the Electrical and Computer Engineering Department at Texas A&M University in the USA. In 2014, he received his PhD degree from Aalborg University in Denmark. Currently, he is with the Department of Energy Technology in Aalborg University as a postdoc. His research interests include grid integration and control of photovoltaic systems in different operating modes, and harmonics and adjustable speed drives in grid-connected power converters. He's also working on reliability of power electronics for next-generation photovoltaic inverters. With that, I'll let you take it away.
Okay. Thanks, Catherine, for the kind introduction. Okay. And hello, everyone. Welcome to this webinar. Today, I'm going to talk about how to mitigate the harmonics induced by dead time in the PWM converters. What I have used is a repetitive control to mitigate those harmonics. Well, in this presentation, firstly, I will talk about the background and motivation of this study. Then I will discuss about the mechanism of dead time harmonics, how those harmonics come from, and then how can we compensate those harmonics. Afterwards, I will present some experimental results to verify those discussions before the conclusion of this presentation. Okay, and as we all know that the power electronics technology has been the enabling technology for the energy conversion, like the energy conversion from the renewable energy systems, for example, the photovoltaic systems and also wind turbine systems. It also provides us a lot of flexibility to handle the input power. For example, we have to maximize the energy production from PV panels, and then we also have to convert those DC power to the alternative current power, that is also AC power. Typically, what we have been using is the pulse width modulation control, as shown in this figure. And sometimes we also need a DC-DC boosted converter stage for the PV applications. However, beyond the flexibility or this controllability, we also have to cope with some side effects brought by the use of power electronics converters. For example, it can generate harmonics that we have to handle with. So regarding the harmonics emissions from power converters, one lies in the intermittency of the energy resources. For example, as shown in this figure, the power injected into the grid is also fluctuating, which thus generates certain harmonics. Another reason for the harmonic emission is that we are using PWM control. Both low order and high frequency harmonics will be generated by the PWM converters. In addition, as non-linear loads are connected to the grid, background distortions will appear in the grid. That's also increase the challenge to control the injected grid current. Thus, we have to develop the harmonic control methods to mitigate the harmonic distortions in the grid current according to some standards, like the IEC standard and the IEEE standards. Okay, speaking of the dead time in PWM converters, why do we need dead time? Let's take a look at the one leg of the full bridge single-phase inverter with bipolar modulation. Here in this slide shows one leg of the full bridge single-phase inverter. And when the inverter output current, the I inverter, is positive, then we want the upper switch to be conducted, and while when the inverter current is negative, we want the lower switch conducts. Thus, the switching pulse applied to the two switches should always be complementary. But sometimes we may have this situation like shown in this figure. and we have both switches are conducted at the same time, then the DC source is short-circuited. This is we don't want this situation happen. Thus, we arbitrarily insert a dead time period at the on states of the switches, as shown in this figure. And doing so, we can prevent the inverter from shooting through, but at the same time, we also introduce harmonic distortions in the inverters and thus in the injected grid current. So we have to develop the harmonic control strategies to compensate those harmonics induced by dead time. Okay, in the following, I will demonstrate the dead time harmonic mechanism on a single-phase full-bridge inverter system. Here in this slide, it shows the hardware schematic and also the current control loop of these systems. We have used the LCL filter considering the THD requirement, that is also the grid current requirement, the current quality of the grid current. And also for the inverter, we have used a bipolar modulation schemes in order to reduce the leakage current generation for the transformer-less PV applications. Again, let's start with one leg of the inverter. As I mentioned, when the inverter current is positive, S1 should be turned on, as shown in this figure, while when the inverter current is negative, S2 should be turned on. Here, in this slide, it shows the complete switching pulses applied to this leg of the inverter when considering the dead time. And we can see there will be voltage loss and gain due to the dead time effect, and thus the inverter output voltage, which is a PWM voltage, is affected by the dead time. So actually we can calculate the voltage change as this equation. According to this equation, it indicates that the voltage change is related to the dead time duration, TD, and also the switching frequency and the DC link voltage, VDC. So this gives some ideas to alleviate the dead time effect by first you can reduce the switching frequency, and then you can also reduce the DC link voltage. Then in that case, the voltage change will be smaller, then the dead time effect will be mitigated or alleviated. More specifically, let's take a look at how the voltage change will distort the inverter output voltage. Here in this slide, it shows the full bridge inverter topology. Since bipolar modulation has been used in this study, which means S1 and S4 will be switched at the same time, while S2 and S3 will be switched at the same time in a complementary way. Thus we can get the output voltage of leg B which is opposite to the voltage of leg A. Simply we can get the inverter output voltage as shown in this equation, and we can see that the dead time will affect the inverter output voltage clearly, as shown in this equation, and where the inverter current polarity will affect the voltage distortion, the dead time duration, and also the switching frequency will affect the inverter output voltage. As I mentioned, this voltage distortion appearing in the inverter output voltage is related to the inverter current polarity, and the voltage distortion level is affected by the dead time duration, the switching frequency, and also the DC link voltage. And so in this figure illustrated how the inverter current polarity will affect the voltage distortion of the inverter output voltage. As we have known that the inverter voltage will be distorted by the dead time, so how this will be propagated to the injected grid current, let's take a look at the simplified model of the LCL filter, which is shown in this figure. We can easily get those equations by applying KVL as shown in this equation, as then we can get the grid current distortion, which is related to the inverter current polarity, the dead time duration, the switching frequency, and also the DC link voltage VDC. So we know that the voltage gain and the voltage loss due to the dead time will pass to the grid current, and thus it is distorted due to the dead time as shown in this equation. So more clearly we can see here is that the current distortion due to dead time is affected by the dead time duration, TD, and in the case of a large dead time duration, the PWM will go into a kind of a square wave modulated mode. And in that case, as shown in this figure, where we can see that some pulses are covered by the dead time because this dead time duration is very large, and then we have some pulses missing in the output voltage of the inverter. Thus, the grid current is distorted. It should be mentioned for those kind of harmonic distortions appearing in the grid current. It is quite difficult to compensate those harmonics using current harmonic controllers. But we have some other solutions to alleviate those kind of distortions, which I will mention in the following slides. So in order to avoid this distortion due to a very large dead time duration, the maximum dead time duration we can calculate it according to this equation, and it thus gives us some ideas to mitigate those harmonics. For example, we can increase the DC link voltage. In that case, then this kind of harmonics can be mitigated. But of course, we also have to apply the harmonic controllers. Well, the output current distortion, I mean the other current distortion reason is the polarity effect from the inverter output current, as shown in this figure. When you can see here, we can see here is when the inverter output current is positive, there will be a voltage reduced. I mean the fundamental voltage of the inverter output will be reduced, while when the inverter current is negative, there will be a slightly increase of the inverter output voltage. But in general, there will be voltage loss in the inverter output voltage. So since the inverter output voltage is PWM voltage, because we are using pulse width modulation scheme control, that's so that the inverter output current will be switching current, which means that there will be multiple polarity changes of the inverter current. This is normally referred to as the zero crossing effect, which will also distort the grid current, as shown in this figure. So in that case, we know that there are two major effects on the grid current distortion. One is the dead time duration. One is the polarity change of the inverter current. So in that case, we have to compensate those harmonic distortions in order to get a better power quality of the injected grid current. So, and according to the above analysis, we have known that the dead time distortion is of high nonlinearity, as shown in this equation. We can further summarize that the injected grid current is affected by the inverter output current polarity, and the dead time duration, the switching frequency, and the DC link voltage. So seen from this equation, and one simple way to compensate the harmonics is directly to calculate the voltage loss or the voltage gain due to the dead time, and those voltage changes can be directly applied to the inverter voltage reference. In that case, we can compensate the harmonics. This is normally the most common way we have been using till now, because it is quite simple, it is more straightforward. But we have some issues when we have a product that the parameters may change during operations. In that case, we have some kind of challenge due to the parameter changes. Then we have to develop those kind of another methods, develop other methods since the parameter changes. So as I mentioned, although the dead time distortion is highly nonlinear, but fortunately the dead time harmonics can be expanded into a Fourier series, which are multiple times of the fundamental frequency. Thus, this Fourier series enables the use of harmonic controllers in the current control loop to compensate the dead time effect. In that case, the harmonic controller can be just plugged into the plugged into fundamental current controllers, which means the harmonic controller is in parallel with the fundamental controllers. Then the harmonics can be compensated. So regarding the harmonic compensators, one solution came to my mind was to use the resonant controllers to compensate the dead time harmonics, since this solution is quite simple and it can effectively compensate the low order harmonics. And however, the low order harmonics which are of interest, for example, the third, the fifth, the seventh harmonics mainly appear in the single phase systems. We can simply parallel the resonant controllers of those harmonic orders, then you can compensate those low order harmonics. And however, since the harmonic compensators are normally configured in parallel, and thus it will introduce a parallel computation burden, especially when we want to compensate higher order harmonics like the 11th harmonics and the 13th harmonics. And another thing is for the resonant controller is that potentially it can trigger the system resonance, and when we are going to compensate the high order harmonics like the 11th and the 13th harmonics. And before I go to the next slide, I want to emphasize here is so the structure of the harmonic compensators using resonant controllers. So you can simply parallel those harmonic compensators with fundamental current controllers. Here in this case, we are using proportional resonant controllers, which can achieve a very good tracking of the fundamental current in the steady state. Well, beyond this solution, another alternative is using the repetitive controller to compensate those harmonics, since it is based on the internal model principle, and thus it can achieve a zero error tracking of any periodic signals without so much computation burden, because it is the controller is in a series connection instead of a parallel operation. So in that case, the systems the computation burden is significantly reduced compared to the multiple resonant controllers. And theoretically, the repetitive controller can fully mitigate all the harmonics below the Nyquist frequency. And as shown in this figure, this bold diagram, and we can see that the PR controllers contains all the internal models of the periodic signals, like the fundamental current, the third harmonics, the fifth, the seventh, etc., and also even the second harmonics in the controllers. Thus, it can fully mitigate all the harmonics below Nyquist frequency. However, it should also be pointed out that a phase lead compensator and a low pass filter, a phase lead compensator GF shown in this figure and a low pass filter QS should be included and also designed appropriately in the harmonic controllers, in the repetitive controllers, in order to improve its robustness, as shown in this figure. So compared with the multiple resonant controllers, the repetitive harmonic controller is also simple because it can just simply being plugged into the fundamental controllers. Here again, we are using proportional resonant controllers, but it can fully mitigate all the harmonics below the Nyquist frequency theoretically. So it is a powerful way to compensate the harmonics in grid-connected applications. All right, and since we have known that the dead-time harmonics mechanism, and also we have introduced the two solutions. One is using multiple resonant controllers. One is using a repetitive controllers to compensate the harmonics, including the dead-time harmonics and also the background distortions and those harmonics appearing in the grid current. So we have to verify those analysis and also discussions. We did experiments on a single-phase full-bridge grid-connected inverter systems. Here shows the schematic of the systems, and we used the proportional resonant controller as the fundamental current controller, as I have mentioned, and then the two harmonic compensators are plugged into the control system in the current control systems, and for the experimental setup, the system is controlled. I mean, the control system is implemented in disk-based systems, and also we used a grid programmable AC power source, which can absorb power from the inverter, and then we can simulate the background distortions and also other grid disturbances which can be commonly seen in the real cases. So we use the AC grid simulators to simulate the background distortions of the grid voltage. In that case, we can verify how robust or how effective those harmonic compensators are. And firstly, we tested the system without any harmonic compensators, which means the system is only controlled by the fundamental current controllers, the proportional resonant controllers. We can clearly see in the results here that there are low-order distortions. For example, the third, the fifth, the seventh harmonics in the grid current, and also, which is the grid current is the red one, and also we can see the dead-time effects are quite significant. There are kind of stairs appearing in the grid current, and this current is not allowed to inject it in the grid because it not meets the doesn't meet the grid connecting requirement, like the THD should be lower than 5% according to the IEEE standard. Then we added the we added the multiple resonant-based harmonic compensators. We can see in the results that the low-order harmonics are reduced to some extent, which means it can the multiple resonant compensators can only achieve a partial mitigation of the dead time effects, because you can clearly see that there is still snares appearing in the grid current IG, and thus we want to further to mitigate those harmonics. Then we tried to compensate the higher order harmonics by ending the 11th order resonant controller. Then the system started to resonate, as shown in the right hand figure, and the system became unstable. So this harmonic compensator failed. In contrast, under the same conditions, the repetitive compensator is plugged into the fundamental, the PR fundamental controllers, and we can see in the results that it can achieve a full mitigation of the dead time effect without any stability issue, as it has been demonstrated in this figure. So the repetitive controllers can also reduce the low-order harmonics significantly, as seen in this figure. Furthermore, we increased the dead time duration. As shown in these slides, the dead time effect appears again in the grid currents, since we increased the dead time duration to be 5.25 microseconds compared to 3.25 microseconds. There's almost two times of the dead time duration, and it means that both the resonant and the repetitive harmonic controllers are not able to compensate the harmonics due to a large dead time, and thus the harmonics appears again in the grid current, as shown in those results. So what we can do to this system or to improve the grid current? Actually, as I have mentioned, increasing the DC link voltage is an alternative. However, as shown in this figure, the resonant compensator cannot achieve a full mitigation of the dead time harmonics. Even the dead time, the harmonics induced by a large dead time at the top of the grid current or the bottom of the grid current is mitigated by increasing the DC link voltage, but there are still other dead time harmonics existing in the grid current, which means that the resonant compensator cannot achieve a full mitigation of the harmonics. While in contrast, the repetitive controller can fully eliminate the harmonics, as shown in this figure, and an almost purely sinusoidal grid current is achieved, which has a very low THD of the grid current. So this is a very good current that can be injected into the grid. Moreover, we also studied the voltage background distortion impact on the controllers. And the first here so the results. We studied the results of the two harmonic compensators in the case of a very highly distorted grid voltage. As we can see here, the repetitive controllers can maintain a very low THD of the injected current, and also the dead time effect is mitigated by the repetitive controller. However, the resonant controllers cannot fully mitigate the dead time effect, although the THD, the current THD is lower than 5%. But this current, we may not, we don't want this current to inject into the grid, because it's going to distort the PCC current, I mean the point of common coupling current, if this current is injected. And also we did other tests under a variety of grid voltage THDs, and shown in these two figures. And also we changed the dead time duration. As we can see here, that the repetitive controller can always maintain a lower THD, and no matter how large the dead time is, and no matter how much the grid voltage is distorted. So in conclusion, when we see those experiments result, we see that the repetitive controllers is a very good solution in terms of harmonic mitigations, including the dead time effects and also the background distortion from the grid voltage. So to sum up, we have analyzed the dead time effect in PWM converters. The analysis is conducted on a single-phase full-bridge inverter systems using where the bipolar modulation scheme is used, considering for transformer-based application. And then we developed repetitive-based harmonic mitigation solutions, and which is compared with the multiple resonant controllers. And we also did experiments to verify those analyses. And it has been shown that the repetitive controller is not difficult to design, while it can achieve a full mitigation of the dead time effects. And here are the key references for this work, and it may be of interest to you. And that's all about my presentation. Thank you all so much.